Networks and System Security Department at ENSA, France. Currently, Professor Al-Kalam research interests are in blockchain-based security policies and models, Internet of Things security, big data security, privacy, evaluation of security mechanisms, and critical infrastructure protection. So Professor Al-Kalam's research spans in a very wide range of topics with more than 150 high-level research papers and has participated in quite a few relevant projects in relation with international and national funding. So thank you, Professor, for your presentation. I think that we now can deliver.
So first of all, I would like to thank the organizer of this conference, this prestigious conference, and also thank all the present peoples. I'm Professor Anas-Aboulkalam, professor at the University of Marrakech, and I will give a talk about security of the tactile internet. I will give an introduction, a brief introduction, then I will give the background, the necessary background to understand the concept of this new field. Afterward, I will extract the requirements and challenges that faces the tactile internet. Then I will present a new protocol, what we call the physical and knowable function based authentication protocol. And finally, I will give some conclusions and perspectives. So what we mean by tactile internet? Actually dedicated to advancing technologies that capture and reproduce various stimuli like sight, hearing, touch, smell, and taste, and capturing these various stimuli from the outside world and let humans as well as machines perceive and react to the combined stimuli in various ways. So an interesting example is the phone, which allows smartphone users to send digital send messages with more than 300,000 unique aroma combinations. Another example is remote presence robots, which consist of a flat screen and video camera mounted on a mobile pedestal. And indeed, nowadays, one important task of everyday life may be increasingly done by a robot. We have the possibility of not only monitoring, but also acting from a remote country like France or Canada, and react or act remotely via the internet in support of our parent, for example, living in Morocco, and so on. So this vision of the internet is now widely known as the so-called tactile internet. A normalized definition is a network or network of network for remotely accessing, perceiving, manipulating, or controlling real or virtual objects or processes in perceived real time by humans or machines. By virtual object, we mean any form of physical entity, including humans, robots, network functions, software, or any connected entities. The tactile internet is now expected to have the potential to create a lot of opportunities and application of our life and our economy. Market analysis have revealed that the potential market of tactile internet could extend to 20 trillion US dollars. Now let's see the evolution or the history, how we came to tactile internet. First, we had mobile internet. In mobile internet, we have a kind of optimized for static or streaming content. We have a round-trip latency sufficient for telephony, web browsing, and video with limited resolution. Then we had the emergence of Internet of Things, which is a kind of interconnections of billions of smart devices, machine-to-machine communications, low rate latency tolerance, and reliability and security. So the transition between mobile internet and the Internet of Things is done through voice and data communication, and also the 5G network, mobile network that enables real-time access to richer content and enable early application of machine-to-machine And once machine became connected, the next natural leap is to have them controlled remotely. And this will generate a completely new paradigm for control communication to steer and control elements of our environment. And now we have the tactile internet. So the tactile internet is a kind of human to machine interaction. So we skip from machine to human to machine interaction with remote control of tactile and haptic machines, control communications, high availability and security, and of course, in this context, ultra-fast reaction time and reliability. Now we have some intersections between IoT, 5G, and tactile internet. So, of course, tactile internet take advantages of the recent advances in IoT and 5G. And the high availability of, and security and reliability of tactile internet will, of course, add a new dimension to human-to-machine interaction by enabling tactile and haptic sensation. So in this context, the 5G network will have to be able to cope with the growth of mobile data traffic, as well as the huge number of volume of data from the smart devices that will power the IoT. And the common important goals of these technologies are very low latency, reliability, the coexistence between human to human and machine to machine connections or interactions, data-centric technologies using Wi-Fi, for example, and of course, security. Now, the global architecture of this kind of tactile internet will have three main components: the master domain, the network domain, and the slave domain, as we can see in this picture. Of course, the kind of data exchanges between master domain and slave domain could be contact location, pressure, vibration, temperature, position, orientation, force, and so on. At first sight, we may identify two or three main levels, like connectivity level and the hardware layer. So in the connectivity layer, we have, of course, the network system and maybe wireless system. And the hardware layer, we have some sensors and actuators, robotic manipulation, and mobile platform. When we go inside this domain, we can identify more layers, like business layer to manage the whole tactile internet system, including, for example, application businesses, profit models, user privacy, and so on. Above, we have the application layer and the processing layer, for example, for storing, analyzing, and processing a big amount of data, employs databases, mainly cloud computing technologies, and so on. Then we have the network layer, for example, for transferring the sensor data between different layers to the network using different protocols and standards. Of course, the pre-processing layer for filtering and so on, and the hardware layer for the sensors, the robotic manipulation, mobile platform, and so on. So in this kind of layers of architecture, we identify some challenges and requirements. Mainly, we have four challenges and requirements. We have a security requirement, latency, of course, reliability, and capacity. In this presentation, we will focus on security, latency, and reliability. So what we mean by latency? So latency is the time interval between action and reaction in a communication channel. In other words, when a data packet is transmitted and returned back to the source, the total time or the global time for the round trip is known as the latency. So it's lower limit is imposed by the communication medium, of course, and it affects the throughput as it is directly related to the amount of data packet that is traveling or transmitted at the given moment. And basically, as we can see in this example, the latency is the sum of 4 delays, like the delay in storage, the device processing, the transmission, and the propagation. We have in this schema an estimation of the acceptable delay in different phases of the communication. Here we have an example of or use case of remote surgery. It is commonly known that the latency in the context of internet must be under 1 millisecond in order to experience true real-time interaction with the environment. And of course, if not, wrong perception will be caused from poor coordination during digital feedback to the human senses. And that will have some catastrophic damages. Then let's focus now on the security challenge. So like any new technology in the next generation network, the information forms the critical thing that should be transmitted, proceed with respect to its confidentiality, integrity, and availability. So the 3 main component properties of security are confidentiality, integrity, and availability. For example, in the medical field, before of the surgeon that wants to perform a real-time surgery on a patient, data should be, of course, available to authorized person like the surgeon. Private data should be not disclosed, so this is a matter of confidentiality. And of course, the information transmitted or proceeded via the Tactile Internet network must not be modified, for example, by man-in-the-middle attack or even accidentally. So security means ensuring confidentiality, integrity, and availability, and security should be applied at the different architecture layer presented before. For example, if we take the transport layer, at the transport layer, UDP provide fast transmission and low delay variation, of course. However, it remains unreliable connectionless transport protocol. And this is not acceptable in Tactile Internet, as any incorrect received packet by the user could result in an incorrect response given back by the remote environment. And inversely, the TCP is a connection-oriented and employs packet transmission in case of packet loss. However, its algorithm lead to a delay, a kind of delay jitter, which is not desired for transferring real-time data in the context of Tactile Internet. And so to ensure haptic data, haptic audio and visual information should be correctly transported, we require a high reliable system with a maximum packet loss probability. And this means new protocol should be created or existing one should be modified. And how strong security is provided depends on how frequently communication occurs, the amount of the data to be handled and communicated, and of course, speed and latency, and around how frequent authentication has to be. And besides that, as performance demands will increase, high efficient security mechanisms will emerge. For example, encryption will add important cost, and performance requirement will, in this case, will not be satisfied. So it is thus so clear that the security challenges for tactile application cannot be met by existing technologies. Moreover, new technology will bring new services, new applications, new network devices, etc., which imply a larger potential attack interface and thus new risks and threats. And breaches or man-in-the-middle attack in use cases like the one presented above, the medical example, will not be acceptable and will be catastrophic in the image of any company, any public organization deploying such technologies, and therefore security must be treated with extreme importance in this area. We thus need a new trust model, a new service delivery model. We should increase privacy concerns and evolve the threat landscape. We talk about the transport layer. Let's talk now, for example, about the network layer. At the network layer, the level of security that is already available in technologies like IPsec, the normalized protocol used in the network layer is IPsec now. So the level of security of IPsec will be enough for most applications at the network layer. But the increase in end-to-end delay caused by implementation and also by encryption will cause conflicts, and quality of service and performance latency requirement will not be met by using the IPsec. So in particular, IPsec will encrypt some information in the network and transport layer, like the IP address, the ports, the number, the protocol, while this data seems necessary for initiating the type of service protocol and thus prevent the quality of security, the quality of service enforcement. So we should arrive to a balance, to a trade-off between security availability on one hand and quality of service, latency and performance in the other hand. And existing mechanism or security mechanism and protocol do not ensure all these requirements. So consequently, in order to meet latency expectation as well as security requirement, it seems more interesting to implement the security mechanism at the physical layer, and that's what we propose in this presentation. So why physical layer? Because hardware security can be used for the generation of random values, the generation and storage of shared secrets, to execute sensitive algorithms in a secure way, to ensure performance, of course, and hardware implementation are tamper resistant, which means that some of attacks will not be active in hardware implementation. We have a lot of kind of hardware implementation. We may have TPM, trusted platform modules, smart card, FPGA, and so on, but not enough because expensive in some cases for personalization. Storage of K in the memory of this kind of technologies will generate security risk, and authentication problems of the chips themselves may occur. So what we need easy manufacturing and low cost, easy query of the chip, counterweight impossible, generation storage of secret of the shared secret between the master and the slave, authentication of the chip possible, enclonability of the chip, integrity, stability, and large variability between chips. We have a lot of acts of research in this sense, but we choose to use the physical enclonable function. Then to guarantee a low delay identification system at the received side, as I said, we propose using specific and faster hardware function, and this kind of function are called physical enclonable function. We propose to use this kind of function for cryptographic key generation, for authentication, architecture authentication, and biometric fingerprint. And up to our knowledge, this concept was never used in or adapted to the context of tactile internet. So this kind of physical acknowledgeable function will add, can be defined as a unique physical feature of a device, just like the biometric features of human beings, like fingerprints. In other words, this kind of function is an expression of an inherent and acknowledgeable and specific features of a physical object. The most important property of this kind of function is that it requires a physical basis and cannot be reproduced using cryptographic functions or cryptographic primitives. And saying that, the idea behind using this kind of acknowledgeable functions, physical acknowledgeable function, in the tactile internet system is that just like human beings, every device will have a unique fingerprints in a form of physical acknowledgeable function, and this unique fingerprint cannot be reproduced and cannot be cloned. Let's see this example. We have the chip and we have the client. So it sends the challenge and we have the answer, and the physical acknowledgeable function is a kind of function that maps a set of challenges to a set of response based on complex physical systems, like we see in this equation. So this, therefore, it can be considered as a function which takes a challenge in the form of string of bit and produces an answer or response in the form of a string of bit. So we represent it as a function P in this example. And the C is the challenge given by the physical acknowledgeable function, and R is the response of this function. So a challenge C and its response from this function is called a challenge response pair. So we answer to this question, is the chip original? Is the chip allowed? How generating shared key? And also, am I able to simulate a chip? Am I able to reproduce the chip? And am I able to find the shared secret? So basically, this physical acknowledgeable function have the following properties in terms of the response. This function produces the same response with the same challenge with high probability, even if the same challenge is used multiple times. Also, the same challenge will produce responses far apart with high probability if it is input to different functions. In our protocol, we use this notation. IDE for the ID of the tactile internet actor or device. We may be able to calculate the hash function. We use the hash function for variable x. This is for the concatenation and so on. And this is our protocol. We have the following steps. In step 1, the tactile internet device send its ID and random. So we have the ID A. ID of A is the identification of this device, and also N1 is a kind of randomly generated norms. So this information are sent from the device to the server. Then in the second step, the server tries to locate this ID of A in its memory. If this search fails, the authentication request, of course, is rejected. Otherwise, the server reads the response This response, of course, is securely stored in its memory for this device, and the server then generates a random number, which we call here RS1, and user RY to form the encrypted message as indicated in this step. The server then sends this information and the hash, the message authentication code, to the tactile internet device, and this hash, this message authentication code will, of course, ensure data integrity and freshness. And the first two parameters in this message authentication code function ensure data integrity, while the last parameters, RS1, serves as the freshness identifier for the server. So the same approach is followed for data integrity, message freshness, and source identifier through the protocol. In the third step, the tactile internet device IDA generates RI using its function and the challenge CI as given in this example. And the device then obtains RS1 using RI and verify the source integrity and freshness of the message using the message authentication code. If the verification fails, the device A terminates, of course, the authentication. Otherwise, it generates a random number, another one, around 2 in this example, and compute the new response RI plus 1 by using the new challenge as indicated. So this new answer or response, challenge response protocol, will be used for future authentication. So this protocol, by using this kind of function, will ensure confidentiality, integrity, availability, and freshness. We also perform some evaluation of our protocol. So here we have a proof that we have a good shared key, and also we proved that we have a good shared key, and also at the server part. So the presented protocol is secure against cloning, of course, because we use a clonable function, and also physical attacks. In terms of complexity, our protocol is the order of n and less than other existing protocols in this field. So in conclusion, the tactile internet will be centered around human-to-machine communication by leveraging devices that enable haptic and tactile sensations. It is similar to IoT and 5G. It demands very low latency, high reliability, coexistence between human-to-human and machine-to-machine, but also integration of data-centric technologies and security. And as the power of machine increases, the tactile internet should help complement human rather than substitute for them, thus empowering them by providing a growth path based on increased output rather than reduced input due to automation. To ensure good latency, performance, and security, a new protocol based on physical and clonable function was presented. We did hardware implementation and evaluation of our protocol. Thank you for your attention.
So thank you very much, Professor Al-Kalam, for your very interesting presentation. I think we do have some time now to answer some of the questions of the audience. First one says, did extremely low latency in combination with high availability, reliability, and security define the character of the tactile internet?
Exactly, exactly, exactly. So actually, uh, communication should have a low latency because of the device and the server will should communicate in a short time in order to the perception of the human will not be modified. So latency is very important. Of course, performance and availability, because if we did, for example, a remote surgery, availability of data, availability of component, availability of information should be important. And of course, security is very important because data, exchanged data should, or processed data should not be modified accidentally or by an attacker. Privacy should be preserved, and so on. So I agree with you. This requirements are very important in the context of tactile internet.
Okay, thank you, Professor. There are more questions. The second one that is being made, this one actually it's been made by Sahil Nabil as well as the previous one. He asks the following: the outlining remaining open challenges for the tactile internet. What do you think?
Yes, of course. Of course, when we talk about 1 millisecond latency, this is, for example, a big challenge because having 1 millisecond between transmission, processing, most of the time is done in cloud environment, and also receiving the information and sending back the answer. All this communication should be done in less than 1 millisecond in order to be well perceived by human and by machine. And this is a big challenge for the moment. All the existing implementation do not satisfy this requirement of latency of 1 millisecond. Security challenges also, so added to latency, security challenges remain open challenges. We address the context of implementing security function on hardware devices, but does not answer all the security challenges. For example, how preserving privacy is another example that should be addressed, and so on. So we address the security challenge just to mix or to find a trade-off between security and latency and minimize the latency, minimize the processing time while ensuring security, and prevent some kind of attacks, and not all the kind of attacks, of course.
Thank you very much. We have a third question, and basically, from what I understand of the question, it's asking about what are the enable technologies for tactile internet, and they put as an example cloud, robotic, and network coding. What do you think? What are the enabling technologies, the main ones?
Yes, of course, using cloud and robotic are enabling tactile internet technologies. I agree with this assumption. Yes, yes.
Okay. There's another question, in this case by Megdad Yassin, which says, are there any existing attacks against tactile internet?
Yes, of course. Yes, of course. I talk about man-in-the-middle attack, for example. This is a kind of classical attack, and we, of course, find this kind of attack in the tactile internet. So all the attacks that we can fight at the server side, at the client side, and at the communication side for any kind of communication, for example, in IoT or in mobile communication, all this kind of attack will be present in the context of tactile internet.
Okay. Another question that is being raised is, what is the main difference between IoT and tactile internet in terms of security?
Yeah, As I said before, all the problems that we find in IoT will be present in tactile internet. Now, the main difference is that the latency requirement that should be addressed in addition to the security should be well studied in the context of tactile internet. So all attacks that we find in IoT will be present in tactile internet, but the solution or the mechanism that will prevent this kind of attack should, in the context of tactile internet, take more latency and performance requirements.
Mm-hmm. Okay, thank you. We have another question. This one is done by Kartit Ali and states, how to share the secret key in the physical layer? How is this done?
Yeah, as I explained in our protocol, the secret key is stored with the message authentication code in the physical layer. So it is protected against disclosure and also against unauthorized modification.
Mm-hmm. Thank you. Thank you very much. So audience, I think that we have a little bit, I mean, we're giving a hard time to Professor Al-Kalam, but if you have any further questions, please feel free to ask them.